then pass the problem on to that subsystem owner, then that developer needs to proceed again to reduce the problem, zoom further in on the root cause, and then solve it. That's all a very long and tedious process. Our desired flow, depicted on the right, in fact indicates that we want to skip this first product indicator altogether. In fact, we want as much debug info in the problem network to be available so that in fact we could send it immediately to the right owner without any pre-analysis. And also that owner of the problem wants to avoid that just to reduce the problem too much. That's also a very time-consuming problem. Ideally, you would know almost immediately where the problem is located and be able to fix it. That's the desired goal. How to reach it? So we first need to detect the software from the crash from inside the software. If the QA tester sees that the V goes down and reboots, it's not so valuable in the sense that there is not much observation which he can have. He has no inside information. He only knows that if he didn't know it's crashed. We want link to that self-detection of crashes, dump as much info on crash as possible, and good tooling to visualize and analyze those crashes and maybe even make the crashes fun. And then continuously improve that tooling so that as time goes by, the software size increases, more and more of those crashes appear in a new software stack, that we have an existing flow to tackle those and proceed to the more difficult problems. That's my final slide on our organization. So the roles are the QA tester, black box testing TPs, during duration tests overnight to weekends, writing contribute codes. Main developers write functional code, follow functional software architecture, and also follow what we call execution architecture rules, which are in fact the more design rules. How do you write real-time software, how do you go about deadlocks, mutexes, stuff like that. And they need to debug, of course, using post-mortem info and debug tooling. The debug info which they get, since these are the normal developers, so to speak, we want it to be very accessible and very readily to be used. The execution architecture team is then blessed with creating the tooling for this post-mortem info and debug. And if a problem is too hard to be tackled by normal developers, the execution architecture team gets it back and can grind their teeth on it. So that also keeps them motivated to baseline the solutions which they see, make new tooling, so that these harder problems also become easy in the long run, and that they also keep their own workload under control. I'd also like to especially thank Nico and Peter who helped this presentation. The one slide overview on fault handling in the software. So first we want to detect faults and do that at various places of exception handlers, signals, enter in a signal handler, so you can program your own signal handler and do some processing from there. It's good to install proper watchdog mechanisms, either if you have a multi-core system, observing the other cores, seeing if they're dead somehow, and using that info as a trigger. Or inside the software, looking at the other threads and processes, whether they're still alive somewhere. So such watchdog tree is very important to be installed. And kernel crashes also end up in an exception handler. So in fact, you also have a central point to handle those. And towards logging information, enormous amount of info which you can gather. So rather the question is what information is useful to be gathered. You can output it in the UART. Various circular buffers can be installed, which you fill with events. Stacks of processes and threads have made tooling to backtrace those. So you see the stack trace and the function calls each other. A lot of standard Linux info, which is exported to /proc, for example, is also useful to be baseline at the moment of a crash, for a user space crash. So you have that as a context. Also memory usage for basis of out-of-memory detection. all of that you can log, and this keeps on growing, in fact, as we get more and more complex problems. This info must be stored for later retrieval. We have an flash to store corresponding nodes. UART logs are stored by diagnostics. And ELCE, we also have some from NVM, which is still an interface to serve to detect hardware. And towards recovery, we have various degrees of reboots. The hardest reboot, you can't recover in other ways, to just go to the system as we call it, so we reset the power cycles and we do complete boot again. We also have some more lightweight reboots, like keep the video flowing, but when we restart the application which has crashed, it gives a fair chance if the customer was just watching some movie that he doesn't even notice if he is rebooting some part of itself. They must be retrieved, those field reports from the field customer side from development, and then analyzed using the show. Okay, then for the next section, examples, software crashes. So I've lined a few up. I'll go through them, and as we go through them, you'll get to know the toolings that we have implemented. So first example, some null pointer dereferencing. So someone is dereferencing a null pointer. The whole process gets a signal. This is detected by installing a signal handler in all applications. So it's a design rule for the applications we write ourselves and also for third parties who make the solution for us. They must look against some deeper shape library and initialize it. And that one does all the job of installing the signal handlers. That one was made by us. The signal handler, in fact, immediately proceeds towards creating a dump in the internal flash with all the observation data. That's just copy this dump to flash from flash, attach it to the problem report, and the analysis is done by automatic translation of the backtrace to the problem report. For the stack backtrace, we have a proprietary solution. It's mainly due to historic reasons because it wasn't available in this backtrace or backtrace. It also has some advantages. At this moment, it is possible to both backtrace user space and even I/O calls and then back into kernel space to have that complete view. Also, we have the possibility to backtrace all of the processes which are running in the system, even the ones which are in an uninterruptible sleep or which are blocked on signals. So even when you have two signals arriving in the process, with the signal still being handled, next signal, all these brief cases, you can still backtrace the processes, not only regarding these fixed states of the process that the system can do. What does such backtrace look like? This is the view which the developer gets at the moment. The problem report talks to his and talks to him. So the stack has already been jumped up. You see the function calls. They're all decoded already. They have the proper function name and even the line numbers of the files. So it's all very easy for them, which is good. So yeah, almost any developer can proceed with this.
Is this your proprietary implementation?
Sorry?
The tool was yet analysed, but I'm sure you've got the backtrace out. This is your proprietary tool.
That's a proprietary tool. So we have the backtrace, which is first grabbed from kernel space and put into a file. That file also is tagged with the version number. Then you have another tool which does the translation, so it knows this, it recognizes this version number. It also knows all the other symbols from the release of that version. So it can do that translation and also attach itself that already in that same debug node, so everything is translated. And then here, this is a web UI, in fact, which presents it a little bit more nicely, and for example, there's a C in the road. So that's a website also which is proprietary.
I like that.
Yeah. So you can see bottom up the stack trace in this case. It's our own code, so it won't say much to you, but there's a text stub. You have data text. At a certain moment, that function add to wanted on the third last line performs the segmentation fault, the null pointer dereferencing. So you see the OXO, and then the exception handler of the signal kicking in, which via that send and receive call triggers the debug to be created and run. So yeah, the guy who did the text receives this. It only takes like a few seconds to recognize whether this is did text, that subsystem. They'll assign it to some guy, and the guy can readily see on that release on line 198. Apparently, there's a null pointer dereferencing, and you can check that line. And effectively, the patch then just consists of adding the proper null pointer checks and doing the proper fix. So the point here is that it takes almost no time to get to the point of that developer looking what he needs to fix at what line, and we are working very efficiently that way. So this explains how we backtrace, in fact, one thread in a signal in a crash. Now, the second example, we're a watchdog, so where work.The is not responding. Our TP software works with work.The, which we call bump engines, and that one executes tasks, which we call bumps. So all tasks must be finished within a certain amount of time. There is one particular task which is also scheduled on that work.The, which needs to feed a watchdog. If the watchdog is not fed within time, also debug dump is triggered. So all the tasks must finish in time. If one task takes too much time, the watchdog won't be fed, and you get an error. Of course, if he's doing a lot of valid number crunching, it should be split up, otherwise the system is broken. So we design a little bit towards it. Individual tasks should not take too much time. After the debug dump is taken, the system is restarted to really avoid that the customer needs to put out the plug and insert it again, because that's really not friendly. So the crash is, for example, a watchdog due to a task which is in an endless loop. Inside that task, it's taking too much time. And the worker needs to feed the watchdog, which is how we detect it. We dump a backtrace of that worker thread, and for example, by raising a signal to that thread, or by just doing it centrally, and then we analyze the backtrace. So it's the same thing. We see the bottom to top, how the calls have gone. Just it's a little bit hard to read it in the blue. Sorry for that. What you see is that we end up at some CPU call X function, which is in fact an RPC call to another probe. So effectively, this task is waiting for another core to finish on the job and is stuck waiting there. And the work cannot continue. Maybe they should have decoupled, knowing that the other guy would take a lot of time, and they should decouple and just wait for notification. Whatever they need to investigate. So it's very easy here to also go to the right owner to investigate why this task is taking so much time. The third example, where a watchdog is locked on another thread. Since we have these applications working with RPC messaging one towards another, it happens in fact quite a lot that most of the crashes, in fact, that the application gets a watchdog, but actually is waiting for another application, might be waiting for another application, so you need a complete system to, in fact, to know what's going on and who's not the real culprit, with all these guys waiting on one another. So our solution here is that in our debug dumps we backtrace all the threads. We don't trace signals to all the threads. It would be a standard solution. In fact, we have from kernel space enumeration of all the threads, even the kernel threads, and we backtrace them all. And we also dump traces of the last events in the system. The analysis then consists of translating these backtraces again and looking at all of them together, and finding root causes. and by looking at this visualization of the last X seconds, which were done. Our tracing of what happens in the system is also again a proprietary tracing format. We started this tooling a long time ago and evolved over time, so it's a good time to look back at what LTD and G are doing, etc., because a lot of things seem to overlap. In the kernel, using trace points, we have this circular buffer which we maintain ourselves, so every time a task switches in the kernel, when an interrupt is handled, we can add traces, syscalls, signals, all of that can be added to the circular buffer. Also events which happen in user space, for example the bump execution, if the same thread keeps on being executed but chooses to switch from one task to another, it's not really an event in kernel space, but still we can push that into that kernel trace buffer and make that event visible so we know at all times what tasks are running. RPC calls between applications. This is also a list which we expand or shrink as the need shows. Visualization then is a modified time doctor. Time doctor is a project which is already open source. So it gives you a graphical user interface to use such information. This is a screenshot of time doctor. On the left you see all the processes and threads in a tree view with a parent-child relationship. They all have sensible names. That's another of those execution architecture rules. If you just see a bit number, it doesn't tell you anything. So we ask by design that everyone names his threads, that we can recognize afterwards what thread was doing something. And then you have the obvious timeline view. You can see what thread was consuming how much CPU at a particular moment. And little colored bars, which you see here, are the worker threads, where you have the individual tasks. So every task has a separate color. And when you hang over them with your mouse cursor, you get some information like this is a task name. Also have these bin bars. Those are individual events which are happening, for example, an RPC being executed or a UART print being made. So it gives an easy way to navigate and see what's happening and zoom in on stuff. If some of the many processes are particularly interesting or related to the problem you're investigating, you can double click on them, they would appear on top. So you have a nice, concise view there of what's of your interest. And for the particular problem which we started on, if some processes are blocked on one another, this is one example. So you see there are 4 processes, each executing some task, but you see that the task keeps on dragging. Apparently they're waiting on one another, not really clear, but they all seem involved in the problem. Then you can zoom in and really see how there's this yellow and this purple ones, which are kind of blocked at the same moment. They make a call to the green one, which is in fact a platform performing some RPC, but yeah, that one seems a little bit later in handling. So this gives you already a view like, okay, it's really these processes that I have to look at. And then you can jump back to the backtrace for those particular processes and see what was actually happening. Again, here it's a little bit difficult to see. Actually, what is happening is that one application was performing a call towards a platform call, which again takes too much time. So it's an RPC. The application is stuck waiting on that RPC. The platform app is doing its stuff, but too slowly. And even another thread in that same application is already pending on some mutex because it also wants to operate on the database which they have in this application. They're all waiting on this mutex to get free, but it's still locked because it's waiting on this RPC towards the bottom of the header. Actually, in this case, you can see that the app gets the watchdog because its watchdog was a little bit off timing or it was maybe a little bit tighter. Platform up is the real culprit, being slow. In this case it was also again stuck on an RPC platform up towards the other core, so the other core was in fact the culprit. So all of that can be nicely and easily investigated using the system. A fourth example, CPU overload. So you don't necessarily need to be stuck on RPCs. Just another task is consuming a lot of CPU. Your own tasks will execute in slow motion, so to speak. And all of those worker threads are feeding their own watchdog, so make it their own watchdog time. So it's the same solutions which we can use. We dump a backtrace of all the threads. We trace the last events. We translate, we visualize. That looks a little bit like this. So you see there that the bottom of the sub is hitting the watchdog, but actually it's not split at all. It's not consuming too much time or being inefficient. It's actually the top one, which is in this case the S2 up, which is consuming these big chunks of CPU, which is pushing the other ones into starvation, in fact. So such visualization makes it easy to see such patterns. The next example, a watchdog due to a deadlock. So the same occurs, this deadlock triggers a watchdog again because the tasks are blocked. Everyone had to feed the watchdog, but one dies out. We again done the backtraces, so that's one lead. But we also have possibility with these events which can be looked if you really are particularly interested in some blocks in the system which are used a lot. For example, you can add an event towards the position of those blocks, and then you can readily see it. So in this case, the Y shows in red error log and weighted messenger 5 log are indicating here. And indeed, if you look at the example itself, you see that in this case it's again some application holding on its database and then trying to perform holding that log in RPC, which requires an RPC log. At the same moment, there's another process which gives a notification via RPC, so it holds that RPC log, and on that notification thread, in fact, they want to acquire the log of that database in output. So they're stuck on one another, and especially since these RPC logs, for example, they're used to be from quite a lot of sites and quite often in the system. So the guys deemed it necessary to particularly observe those. If some logs are in the game, like for example the up log, which are not specifically tagged by the tooling, you can still look at the files and the functions in the game and ultimately see that it is acquiring a log, it is doing an RPC call. So they're all hanging around those particular functions and files. So it's not too difficult also to find what other logs are involved. Last example, out of memory. So the problem with Linux out of memory, if at a certain moment Linux runs out of physical memory, tries to free up physical memory, which is not available, it will just start and shoot off random or semi-random processes until it again has enough memory. For our TV applications, all of these applications are so much intertwined and hooked together, this would anyhow be fatal. But moreover, since particular applications are shut down, we don't have the forensic evidence anymore on what state they were in and how much memory they were consuming. So what we did is collect some evidence before, in fact, the out-of-memory killer kicks in. So we poll the free memory, we have some heuristic value based on some /pro files. So, okay, this is the amount of memory which you say you are using, this is the amount of memory which you say that you're having crashes. It's almost 100% clear. It's good enough to say, okay, it's almost hitting the out of memory. We need to keep some margin. Anyhow, our system was designed to consume even less memory. So this is a good moment to chop it off and make a complete debug dump and analyze who was consuming too much memory. So we poll the free memory, like this every 10 seconds, say. We validate that heuristic value. If we seem to have not enough memory, we just pause a debug dump and we dump the memory status. This memory status is also proprietary tool parsing TPVision. We get such kind of report from it, but that's really the physical memory which we're talking about, not the virtual memory. The chance of getting out of virtual memory is rather low. It's a process having 4 gigabytes. It's really kind of obvious if you're misusing that. We're only looking at what is actually paged in. At such a moment, in fact, we're already kind of in memory cache, so you see that quite a lot of text is already paged out, and Unix is constantly paging out pages to page in another one. So you get this kind of work from a real physical memory usage. Also, libraries are mentioned separately, since they may be used in the context of multiple applications. They're only consuming memory physically once. So they're mentioned separately. At this moment, you see that the guy called TPVision is having a consumption of 240 megabytes, which was totally out of spec or out of intended use. And as a culprit in this case, this view is just another text file in the debug dump. So the first guy analyzing the debug dump just needs to look around a little bit. If he suspects an out of memory, you can just look at this and immediately assign it to TPVision. We'll probably have a hard time to find out next time. I hope these examples have given you a little bit view on how we deal with things, what tools we have, and how we use them in different roles in the organization to investigate this. The crucial thing here is that we want to minimize the time and optimize the efficiency of investigating crashes. And that way we can solve more crashes on a given day and reduce time to market. We're continuously improving this based on experience. Question time.
This process that you described is used for doing the key right before you deploy it in the market. What you guys do after you go to the market, you put your TV on the market, and there's some crash in there? How do you figure out together the problem?
The nicest mechanism that we have is that if a customer would call service and say, look, my TV is really behaving weird in my particular home circumstance, they have a method to, the customer needs to type in some key code, and that will trigger the debug dumps to be sent to the service center, who can collect the data, and the most serious problems, which is in a lot of customers, those end up in the developer center again, along with those debug dumps. You can investigate those and get a view on what's happening. This is much better than the service guy needing to come to the home premises, which is expensive. Also, in fact, we're launching products, we know what software we're launching it with, and we're still updating that software afterwards. So there's also software updates which can be sent to the customer. So if he chooses to upgrade his software, he will also get a lot of fixes which we implemented later on. So that's another way for him to get fixes.
So you keep these tools enabled in the production even after the QA. You keep your tools for debugging or enable it some kernel compilation, you'll deploy that to the product.
Mathieu, our software completely runs all those diagnosis tools, and they keep being active in the field. So it's exactly the same thing. Otherwise, you've seen already, you can't solve the last bug in your software because you need to send the product to the market. The moment you would switch off your debug infrastructure, it's adapt to real-time behavior of your system. So there's some bugs which were not happening a lot before might suddenly happening a lot afterwards. So it's a risk in itself which we don't want. And it's also nice to get this diagnostic.
So crashes and hangouts are easy to detect. Do you have any solution for drive problems and for recording problems? Like if I switch to a channel and instead of picture, I see some blurry stuff. Is it possible to detect and record that?
It depends on the root cause of the blurry stuff which you're referring to. For example, the signal strength is too low on the cable or on the air. Maybe that knowledge is available somewhere in the TV.
So, but you basically don't do anything on crashes.
We have our own system of printing, so we kind of adopted the printing mechanism inside the kernel where you can have the severity. We kind of adopted that in userspace, and also we added an extra tag which indicates the feature to which this print is related. So this allows, in fact, if, for example, the tester is testing installation or video quality, let's say first, okay, I want all the prints related to this feature, and maybe also the debug prints, not only the very serious ones, I also want them available in my UI code. So that way, the developers can add a lot of prints, which are filed out and not needed, those which are enabled if they are needed. I think that's the only way to find such problems.
You have this proprietary solution when you release that somehow for open source. One more question that I have is, for what kind of platform does your debugging tools work? I mean, ARM or MIPS, but there are some other architectures for TV that can be used, like SH4. Does this tool work for this?
At this moment, they were developed for MIPS, and latest update which we did was to support asymmetric view, of course, to make sure that we have a good view of what's happening to the course there. The user space part is really linked into our commercial software, right? The kernel space part, of course, is a kernel module that's open source. We also ship it to our customers if they ask for the open source, which we have in TV, we have regulars, which we ship on as a CD-ROM to them. The first question was towards...
Don't you release the tools that you use for open source?
This time doctor tool, that one is already available. So anyone who uses it, in fact, if you feed it with the correct file format and the correct data in that file format, you can use it as is.
And what file format is that?
TDR, and it's also something which is proprietary made back in the days on the open source tool, but it's described there, so if you want to adopt the tool, if you like the feature set, but then again, we are using it because it's kind of legacy and we're used to using it. If you're a new adopter, I think you would first try and see that the other solutions which are going to be really open standard and auto fund for the users. Okay, any other questions? Okay, thanks a lot then.